Morning, everybody. This is your e-learning lesson for Wednesday, January 16th. We're just going to be introducing this last little part of section 4.2 where we're going to actually look at the what we call the area problem today. We'll be approximating the area of a region under the graph of a function using rectangles. So I'm going to show you a picture similar to one we introduced to you a couple of days ago. Here's the graph of a function. Now this is labeled as a velocity function, but really let's just think of it in general now as a continuous curve. And if I were to shade in all the space under here, we might be interested in what the area is. And one of the things I showed you to do that we can do is to approximately find this by drawing a series of rectangles underneath the curve. Now I'm moving these as if these are what we would call the left-sided rectangles, where it's the upper left corner that touches the curve. So on all four of these rectangles, the upper left corner is touching the function at those marked points. Now I'm going to take the green ones and draw them just a little differently. This time I'm going to pick the right corner to be the point that touches the curve. So they're drawn this way. So the three green rectangles I would call right-sided rectangles because the upper right corner is the one touching the curve this time. And then this final set of blue ones I'm going to draw in a different way. What I'm going to do this time is try and hit the curve exactly halfway between the two red points. So if this is between the x values 3.5 and 4, I'm going to try and hit it at the curve exactly at about 3 1/4. So about right there. This one is between 4 and 4.5, so I'm going to try and make sure I hit the curve right at about 4 1/4. And this one's between 4.5 and 5, so at about 4 3/4, I'm going to try and make sure I get to the curve. And these I would call midpoint rectangles. It's the very middle of each of the subintervals that I'm hitting the curve at. We're going to attempt to show you how to set up a calculation to do each of these types of approximations. And so let's just make a definition first. Actually, I should go back to my picture and write it on here. No matter which of the types of rectangles we're drawing, the area of a rectangle is the same. I take the base times the height. So the width is the span along the base of each rectangle. And I would label that delta x between any two of these marks. The height of the rectangle is measured by the function. Now it might be measured at the left side like this one is. It might be measured at the right side or in the middle, but either way the height of the rectangle is a function value. And so I'm going to call that f of c. So the c value might be the leftmost point in the subinterval. It might be the rightmost point, as is in the green ones, or it might be any other point in between, for example, the midpoint. The base is the change in x. And then to approximately get the area under this entire span, we just want to add this all together. So in this case, I've got 3, 4, 5, 6, 7. I've got 10 rectangles here, so there should be a sum from 1 to 10. And we would just take each appropriate function value multiplied by the width of the rectangle and add that together. So the area we're trying to measure is approximately this. And so now we'll just fill it in on our definition screen here, that the area under the graph of a function between x equals a and x equals b is approximately found by this expression here. The sum of all the rectangles, the n rectangles, each one has the height measured at some point along the graph of the function, and each one has a width delta x. We could subscript these to the delta x's, and they could all be different each time. However, in the examples today, all the delta x's will be the same, where the value c sub I is any point in each of the subintervals between a and b. So we usually will use the left, the right, or the midpoint. And we're going to do a demonstration of each one today. So some of the slides you're going to look at today might be a little different than what you see in your Canvas notes. I've tried to consolidate some of them down a little bit, and I've added a couple of diagrams to them as well. So the example we have here is we're going to draw the graph of the function x squared plus x plus 1. I've gone ahead and copied this picture from my graphing calculator, and we're looking only at the interval 0, 4. So I'm going to mark that on the diagram here. Here's x equals 0, and then we're counting by ones. So 1, 2, 3, 4. 4 is right here. And we wish to try and draw 4 rectangles. Now, before I actually draw the rectangles, we can see that they'll each be 1 unit wide. So we're going to go from 0 to 1 to 2 to 3. And so to know what the change in, basically to know what the width of the rectangles are, you would just take the entire interval 0, 4, find out how wide that is. Now, if it wasn't obvious, we could take 4 minus 0, and then we're going to divide that by the 4 rectangles. So 4 divided by 4 is 1, telling us that every rectangle will be 1 unit wide. And the next thing I need to do is to find out how high the rectangles will be. And to do this, I'm just going to make a single table that measures the function at all the necessary points. We're going to start at 0, and because our rectangles are 1 unit wide, we're going to count by ones until I get to 4. So we're now going to evaluate the function of these 5 numbers. F of 0, 0 squared plus 0 plus 1. F of 1, 1 squared plus 1 plus 1. It's 3. F of 2, 2 squared, which is 4. 4 plus 2 is 6. 6 plus 1 is 7. For 3, it'll be 9 plus 3, which is 12. 12 plus 1 is 13. And for 4, 16 plus 4 is 20, plus 1 is 21. So our highest point up here is the point 421. Now I'm going to draw on the diagram what I call the right sum, which means to draw the 4 rectangles, but on each of the subintervals that are 1 unit wide, I would mark the rightmost point, which for the first interval 0, 1, that would be at 1. And then my rectangle will have that height and go down. The second rectangle is between 1 and 2, and so I would use the 2, find the point on the graph, and then draw it across all the way from 1 to 2. From 3, do the same thing, and 4, finally do the same thing. So all I'm really going to do is find the area of the 4 rectangles and add them together. And so my sum here is to add together the appropriate function values times delta x, each time for the width, and we're going to add up 4 of these because I have 4 rectangles. And I can even make a note to myself, in this example with the right sum, the 4 values I'm putting into the function are going to be the 4 right sides of each rectangle. So that's going to be the x values 1, 2, 3, 4. So each rectangle will have a width of 1. And so I'm literally going to write out the sum and then just add the numbers together. So the first rectangle is between 0 and 1. I'm using f of 1, and then the delta x is 1. The second rectangle, the height of it is f of 2, and the width is 1. The third rectangle, the height is f of 3, and the width is 1. And the fourth rectangle, the height is measured at 4, f of 4, and the width is 1. So notice, since we're just multiplying everything by 1 here, I'm literally going to be adding up the last 4 numbers in the table. I'm going to be adding 3 plus 7 plus 13 plus 21. You can either use your calculator to do that or add in your head. 3 plus 7 plus 13 plus 21. And I've got the total answer here, 44. By having drawn the rectangles, you can observe right away every rectangle lies partially above the curve, so this is an overestimate. We know the real shaded in area underneath the graph will be lower than that. I'm now going to erase the drawing here of the rectangles and redraw the left sum. And so let's just go erase that part. And now I'm going to draw the left sum, which means on each interval I will pick the leftmost point to mark the height of the rectangle. So all of these then will lie underneath the curve. Our definition is the same in a way. We're adding up the 4 rectangles. So the sum of the 4 rectangles, height times width. But this time, the C values, the 4 values we're putting into the function will be the leftmost points. So 0, 1, 2, and 3. So my sum is f of 0 times 1, f of 1 times 1, f of 2 times 1, and f of 3 times 1. So adding together 1 plus 3 plus 7 plus 13, I'm going to get 24. Because the drawing shows all the rectangles lie below the curve, obviously, and then no, this answer is too small. So the exact answer, all we can do for now is say the exact answer of the area underneath the graph is something between 24 and 44. A good way to get a better estimate might be just to average the two numbers together. But for now, all we wanted was the right sum and the left sum. So the right sum is 44, the left sum is 24.